Good morning, student. Today we shall start the chapter, the theory of congruences. Already we have studied the divisibility theory of integer. Using the divisibility of theory of integer, we shall study the congruences. In today's lecture, at first we shall see the definition of congruences and then some basic properties of congruences. The theory of congruences was introduced by Carl Friedrich Gauss, one of the great mathematicians. In this chapter, we continue the study of divisibility, but slightly different point of view. That is, we shall study the divisibility in the form of congruences. Now, definition of congruences. Let n be a fixed positive integer. Two integers a and b are said to be congruent to modulo n if n divides the difference a minus b, and we write a is congruent to b mod n. That means if we consider two integers a and b and n is a fixed positive integer, if the difference a minus b is divisible by the integer n, that is n divides a minus b, then we say that a is congruent to b mod n, and we write this in this form: a is congruent to b mod n. If the difference a minus b is not divisible by n, we say that a is not congruent to b mod n, and we write a is not congruent to b mod n, that is a slash on the symbol congruence. Remark: if a is congruent to b mod n, then by definition n divides a minus b. Now apply the definition of divisibility. N divides a minus b means a minus b is equals to kn for some integer k. That means, in other words, the congruence a is congruent to b mod n implies that a minus b is equals to kn. For example, if we consider n is equals to 7, then we know that 7 divides 3 minus 24, because 3 minus 24 is minus 21, and we know that minus 21 is divisible by 7, and therefore we can write this as a 3 is congruent to 24 mod 7. Similarly, 7 divides minus 31 minus 11, because minus 31 and minus 11 is equals to minus 42, and we know that minus 42 is divisible by 7, and therefore we can write minus 31 is congruent to 1 mod 7. In the same manner, 7 divides minus 15 minus of minus 64, because minus of minus 64 is plus 64, and minus 15, this will become 49, and we know that 7 divides 49, therefore minus 15 is congruent to minus 64 mod 7. Okay. Now we shall define the residue system modulo n. Collection of n integers denoted by a1, a2, dash dash up to an is said to form a complete system of residues modulo n to one and only one of ak. That means the integers a1, a2, an are congruent modulo n to 0, 1, 2 up to n minus 1. That means if we consider the integers a1, a2, an, the integers a1, a2, an are congruent to any one of the integers 0 to n minus 1 taken in some order. That means a1 is congruent to any one of the integer 0 to n minus 1. A2 is congruent to remaining any one of the integer 0 to n minus 1 and continuing like this. Then we say that A1, A2, An forms a complete system of residue modulo n. For example, if n is equal to 7, then you can observe these congruences. Minus 12 is congruent to 2 mod 7 because here if we compare with A is congruent to B mod n, that means n is equals to 7, A is equals to minus 12 and B is equals to 2. Now when A is congruent to B mod n, if n divides the difference A minus B, here A minus B is minus 12 minus 2, minus 12 minus 2, minus 12 minus of minus 2, because you have to write this on left side. It will become minus 12 minus 2, it will become minus 14, and we know that 7 divides minus 14, therefore minus 12 is congruent to 2 mod 7. Similarly, minus 4 is congruent to 3 mod 7. You can observe this because A minus B means 4 minus 3, it will become minus 7, and we know that 7 is divisible by 7, therefore minus 4 is congruent to 3 mod 7. And similarly, all these congruences are true. You can verify taking the difference and dividing by 7. Here we observe that n is equals to 7. That means the integer from 0 to n minus 1, that means 0 to 6 must be congruent to some integers taken in different order. That means here 0 is congruent to 91 mod 7, 1 is congruent to 21 mod 7, 2 is congruent to minus 12 mod 7, 3 is congruent to minus 4 mod 7, 4 is congruent to 11 mod 7, 5 is congruent to 82 mod 7, and 6 is congruent to 13 mod 7. That means the integers minus 12, minus 4 up to 91 forms a complete system of residue modulo 7, because the integer 0 to 6 are congruent to the integers minus 12, minus 4, minus 11, 13, 22, 82, 91, different taken in some order, and therefore these integer forms a complete residue system of modulo 7. Theorem: for in arbitrary integer a and b, A is congruent to B mod n if and only if the same non-negative A and B leaves the same non-negative remainder when divided by n. Try to understand the meaning of the statement. Means if you consider two integers A and B, and the A is congruent to B mod n, A will be congruent to B mod n if when we divide A and B by n, means A divided by n, similarly B divided by n. After dividing A by n, we get some particular remainder. Similarly, after dividing B by n, we get some particular remainder. But if A is congruent to B mod n, these two remainder must be same. Or conversely, if A and B leaves the same non-negative remainder, then A must be congruent to B mod n. At first, we shall assume that A is congruent to B mod n. Now, A is congruent to B mod n, that means n divides the difference A minus B. N divides the difference A minus B. By the definition of divisibility, this implies A minus B is equals to Kn for some integer k. Then transfer this B on right side, which will become A is congruent to, A is equals to B plus Kn. We call this as the first equation. Now when we divide B by n, we get some particular remainder. Suppose that remainder is r, and by division algorithm, we write b is equals to qn plus r, where q is a quotient and r is a remainder. That means our assumption is that when we divide b by n, we get the remainder r and quotient q. Now put the value of b in equation 1. You can observe that b is equal to qn plus r. After putting here, you will get a is equals to this equation, and after simplifying, you will get this as a q plus k into n plus r. That means taking n common. That means a is equals to q plus k into n plus r. Now again we shall apply the division algorithm, taking q plus k as a quotient and r as a remainder. That means when we divide a by n, we get remainder r. Already we know that when we divide b by n, we get the remainder r. Similarly, after dividing a by n, we get the remainder r. Means when we divide a and b by n, we get the same remainder r. Means we show that a has the same remainder as in b. Now we shall prove the converse part. In converse part, we shall suppose that a and b leaves the same non-negative remainder when divided by n. Means when a divided by n, we shall assume that q1 is a quotient and r is a remainder. And for when we divide b by n, q2 is a quotient and r is a remainder. Means by division algorithm, we write as a is equals to q1 n plus r and b is equals to q2 n plus r. In both cases, 0 is less than or equal to r is less than n. Now here we want to prove that a is congruent to b mod n. To prove that a is congruent to b mod n, we have to prove that n divides the difference a minus b. For that purpose, take the difference a minus b from these two equations, put the value of a and b here. Then you can observe that this r will be get cancelled and take n common. You can observe this simplification, very simple. We get a minus b is equals to q1 minus q2 into n. Okay? That means n divides a minus b, because a minus b is equal to q1 minus q2 into n. That is, there is no remainder. That means perfect division. Hence n divides a minus b, and n divides a minus b in the form of congruence can be written as a is congruent to b mod n. This completes the proof of theorem. Now we shall study some basic properties of congruencies. Let n be a fixed and a, b, c, d be arbitrary integers. Then the following properties holds. First, a is congruent to a mod n. That means every integer is congruent to itself mod n. Second, a is congruent to b mod n, then b is also congruent to a mod n. Third, if a is congruent to b mod n, b is congruent to c mod n, then first integer a is congruent to third integer c mod n. And in fourth, if a is congruent to b mod n, c is congruent to d mod n, then first a plus c is congruent to this b plus d mod n. Means sum of first two integer is equal to sum of next two integer. Similarly, we can take the product also. That is, AC is congruent to BD mod n. And fifth is A is congruent to B mod n, then A plus C is congruent to B plus C mod n, and AC is congruent to BC mod n. Fifth is nothing but same as fourth. In fourth, two congruences are given. In fifth, only one congruence is given. And to prove this, we shall consider second congruence as C is congruent to C mod n. Okay, this is true by first. A is congruent to A mod n. It can be written as C is congruent to C mod n. Okay, and last, if A is congruent to B mod n, then A raised to K is congruent to B raised to K mod n for any positive integer K. Now, proofs are very simple. Only how to remember definition of congruences. Now, in first case, we have to prove that every integer is congruent to itself. Now, proof of first. In first, we have to prove that A is congruent to A mod n. But we know that n divides 0. 0 can be written as A minus A. Means n divides A minus A. N divides A minus A is congruent to A mod n. That means every integer is congruent to itself. Then proof of second. In second, we have to prove that if A is congruent to B mod n, then B is also congruent to A mod n. Now consider A is congruent to B mod n. Then by definition of congruence, n divides A minus B. N divides A minus B means n divides minus of minus A minus B. Means if we know that if 5 divides 10, 5 also divides minus 10. Therefore, if n divides A minus B, we can write n divides minus of A minus B. But minus of A minus B can be written as n divides B minus A. And n divides B minus A by the definition of congruence can be written as B is congruent to A mod n. Okay, that means if A is congruent to B mod n, then B is also congruent to A mod n. This completes the proof of second. Now proof of third. What is the third result or third property? If A is congruent to B mod n and B is congruent to C mod n, then we have to prove that first integer A is congruent to third integer C mod n. Now A is congruent to B mod n implies n divides A minus B. Similarly, B is congruent to C mod n implies n divides B minus C. Now n divides A minus B and n divides B minus C. Then adding this means we know that if A divides B and A divides C, then A divides Bx plus Cy. In the divisibility, in the chapter divisibility, we have seen that taking x and y as a 1, that adding these two, n divides A minus B plus B minus C. And then minus B plus C gets cancelled. We get n divides A minus C. N divides A minus C means A is congruent to C mod n. Okay, this is a proof of third. Then fourth. In fourth, there are two parts. In first part, if A is congruent to B mod n and C is congruent to D mod n, then we have to prove that A plus C, first integer, is congruent to B plus D, that is second integer, modulo n. Now, by the definition of congruence, A is congruent to B mod means n divides A minus B. Also, C is congruent to D mod means n divides C minus D. Now, again, taking the sum, n divides A minus B plus C minus D. That means in the result, n divides AX plus BY, taking x and y as a 1. Here, n divides A minus B plus C minus D. It can be written as A minus B plus C minus D is written as A plus C minus of B plus D, taking minus sign common, means we get n divides A plus C minus B plus D, and by the definition of divisibility, this implies that A plus C is congruent to B plus D mod n. Now to prove the second part, in second part AC is congruent to BD mod N. We have to prove this. AC is congruent to BD mod N. Now first two steps are same. Here N divides A minus B, N divides C minus D. Now in previous case we have taken the addition of A minus B and C minus D. Now here multiply A minus B by C and C minus D by B and take the addition. Means in the result N divides AX plus by, or a divides bx plus cy, taking x as a c and y as a b. Okay, means multiplying by c here, multiplying by b here, and taking addition, we get n divides a minus b plus a minus b c plus c minus d into b for some integer b and c. Now multiplying by C and B, that means simplifying, we get AC, N divides AC minus BC plus BC minus BD. Minus BC plus BC get cancelled and we get N divides AC minus BD, and by the definition of congruence this implies AC is congruent to BD mod N. Okay. Now in fifth, it is only given that A is congruent to B mod N, and then we have to prove that instead of this A plus C is B plus D, we have to prove that A plus C is congruent to B plus C mod N, and AC is congruent to BC mod N. That means here first congruence is A is congruent to B mod N, which is given in fifth. Second congruence is not given as C is congruent to D mod N. But here we observe that in both sides C is there, means we shall consider the congruence C is congruent to C mod N. Means A is congruent to B mod N, C is congruent to B mod N. Here we have taken C is congruent to C mod N, which is not given in the statement, but by using first, we know that every integer is congruent to itself. Therefore, C is an integer. Therefore, C is congruent to C mod N. And then by using 4, this A plus C is congruent to B plus C mod N. And AC is congruent to BC mod N. This is simple only use of result 4. Then 6th result. In this result, if A is congruent to B mod N, then we have to prove that A raised to K is congruent to B raised to K mod N. That means multiplying the congruence itself K times. This result is proved by using mathematical induction. What is the mathematical induction? If any result true for n is equals to 1, means, and then assume that it is true for n is equals to k, and we are able to prove that it is also true for n is equals to k plus 1. It is true for every n. This is a mathematical induction. Now here A is congruent to B mod N, that means statement is true for k is equals to 1. Okay, assume that it is true for some fixed k, that is k is equal to 1, means A is congruent to B mod N. It is true for some fixed k, means A raised to k is congruent to B raised to k mod N. Now A is congruent to B mod N and A raised to k is congruent to B raised to k mod N implies A, means taking multiplication of left hand side, A raised to k is congruent to B raised to k mod N. Means we have written this using the result that A is congruent to B mod N, result 4. A is congruent to B mod N and C is congruent to D mod N implies that AC is congruent to BD mod N. That means there is multiplication of left hand side and right hand side. That is, in this case we get A raised to k is congruent to B raised to k mod N. This implies A raised to k plus 1 is congruent to B raised to k plus 1 mod N. Thus the statement is true for k is equals to 1 and hence it is true for every integer k. That means a raised to k is congruent to b raised to k mod n for any positive integer k. These are the properties, 6 properties. You have to remember this. To solve some problem, we are required these properties. Now next theorem, if CA is congruent to CB mod n, then A is congruent to B mod n divided by D, where D is the greatest common divisor of C and n. Student, observe this. This means that we cannot cancel C on both sides. Here CA is congruent to CB mod n. We can't write this as A is congruent to B mod n. Instead of that, we can write A is congruent to B mod n by D, where D is the greatest common divisor of C and n. Now to prove this, we shall consider CA is congruent to CB mod n. Apply the definition of congruence. This means n divides the difference CA minus CB. By the definition of divisibility, n divides CA minus CB implies that CA minus CB is equals to Kn for some integer k. On left side, take C common and call this as equation 1. C A minus B is equals to Kn. Now it is given that in the statement D is the greatest common divisor of C and n. Therefore, there exists relatively prime integer R and S satisfying C is equals to dr and n is equal to ds. Now in equation 1, substitute the value of C and n. On left side there is a C and value of C is dr, and on the right side there is a n, value of n is a ds. Substituting values, we get the equation dr A minus B is equals to K ds. Observe that on both sides there is a D, cancelling D on both sides. This implies that R into A minus B is equal to K s. This means if we consider K is some integer, we observe that by definition of divisibility, this implies that S divides the difference R into the difference A minus B. Now here S and R are relatively prime integers. That means GCD of S and R is 1. Therefore, by applying Euclid's lemma, S divides R A minus B and GCD of RS is equal to 1 implies that S divides A minus B. Try to understand remember the Euclid's lemma which we have studied in the divisibility theory. S divides A minus B means A is congruent to B mod S. But S is a n by D because here